Thank you for joining this session. It's the first day at INTERGEO, so obviously an exciting day for all of us. I am a director at a company called Teledyne, and the part of the business that I'm involved in is in designing and manufacturing industrial-grade cameras for a wide variety of growth segments, including, of course, the geospatial industry. One of my products is a spherical imaging product, so I'm happy to share with you more about that a little bit later in the presentation. But what I wanted to talk to you about today is some of the advancements that we are bringing to the table. So that's why we've called it Beyond Resolution, Advancing Mobile Mapping Through Spherical Imaging Innovation. One of the questions that we often get at the start of a conversation is, what resolution of the imaging systems do you have to offer us? And so we get into a conversation about imaging, we talk about mobile mapping, and we talk about what it is that the customer is trying to achieve. What are you trying to achieve for yourself, and what are you trying to achieve for your client? So I'm going to start with an opening question here. What if image resolution is not enough in the mobile mapping context? Just give that a thought for a moment. So one of the things you might say is, what if it's not enough for what? And of course, many of you, I think, are probably aware of mobile mapping. Maybe not everybody is. So I'm just going to take a moment to touch upon the process and systems of mobile mapping in the way that we see it, so you understand where we're coming from. Okay? So mobile mapping is the process of collecting geospatial data from a moving platform, typically a vehicle. And that system, or that process is using a range of sensors. The sensor technologies capture a range of different types of data types, but it's doing this in a rapid, high-resolution capture of the physical world. Remember, we're trying to capture what's really out there. And at a high level, this process allows you, of course, to generate 3D models, maps, and of course, high-resolution imagery of roads, cities, and natural environments. Right? So that's a high level at the process. The systems themselves, once you capture this information, what can you do with it? How do you make use of this information? Right? So you're able to digitize road networks. You're able to perform asset management, figure out your maintenance activities. You're able to support urban planning, to think about roads, buildings, and infrastructure. Right? Of course, monitoring environmental changes. That's the beauty of doing mobile mapping, and you've got a temporal, like some separation in time to notice the difference in change in the environment. And of course, enable transportation analysis. Understand road and infrastructure, think about signage, where roadways are open, where are they blocked, perform optimization and planning. Right? So these are the capabilities of mobile mapping, the mobile mapping systems, and what they enable for customers. I see some nodding heads, so that makes sense to everybody. Okay, now think about spherical imaging now. What does spherical imaging bring to the table? Well, for mobile mapping, it's capturing the entire 360 view, right? That's the entire sphere, spherical imaging. And why is that important? Well, if you're a planner or an engineer, you're providing context to the entire space to where you maybe have specific sensors capturing data. So context is really important. What else are we doing? We provide the capability of visual inspection. So when you capture this data and you capture it at the resolution and the spatial accuracy that's required, now you can do inspection remotely. You don't have to send people on site to do that next level of inspection. And of course, change detection. We talked about that for a moment here. If you're able to go and monitor the change, you can see change in traffic flow. You can see the change in your environment. We have customers that are out there using this system to monitor the change in the vegetation within cities, because certain cities have to have certain type of requirements in terms of the green space. So just being able to monitor that through the seasons year after year is a really important part of their business. So mobile mapping enables all these capabilities, and spherical imaging is a big contributor to supporting those application use cases. But where are the true benefits at a high level of mobile mapping as a process in terms of the systems and incorporating spherical imaging? It's about allowing governments engineers and private firms to make faster data-driven decisions, right? Faster data-driven decisions while reducing costs and improving safety. This is the true benefit of this technology, these processes and these systems that are making a difference in our market, and it's driving growth in where we are right now in the in this representative show in the geospatial industry. Does that make sense to everybody? Process, systems, spherical imaging, and ultimately, what are we trying to do? How does this benefit us as a society? However, let's go back to resolution. I would propose to you that image resolution is necessary to get the level of detail that you require to support these applications. But it is not sufficient. Ultimately, what you're trying to do is get usable, geospatially accurate data as part of this overall process in order to derive those benefits we spoke about. That's really what you're trying to do. And of course, when it comes to imagery, one of the challenges is that this is mobile mapping. So you're moving. You're capturing image data on a moving platform. And this can result in a number of different challenges. Of course, you're moving, so there's motion blur. We have this thing called this very bright light source in the sky called the sun, which you cannot avoid when you're mobile mapping outdoors. And of course, that can create very bright areas in your scene and very dark, dim, high contrast areas in the scene, which means you lose information because of that broad range spectrum of that very bright light source. That makes it very difficult to get the right exposure to the scene, so you're maximizing the amount of information that you're deriving each time you're capturing your frame while you're actually moving. And of course, electro-optical systems like camera systems have lenses. Lenses are made up of multiple optical elements, and that creates artifacts like lens flare. So these are just example challenges that make it difficult to get the most information out of the imaging part when you have a mobile mapping system. So let's look at that first point, resolution. I think we can establish, and I'll take one moment here to establish that resolution does matter. Right, so we're looking at this beautiful scene here, and we have two cameras mounted of different resolution, and we're going to hone in on that vehicle on the right-hand side, that vehicle and that signage here. So let's just have a look here. And you can see we were probably about 12 meters away from that vehicle. And if you look at a 30 megapixel image all around versus a 72 megapixel image on the right-hand side, even to us visually, with a human eye, you can see that there's an apparent difference in your ability to do things like discern the letters, the alphanumeric characters in that license plate, or read the characters on that sign on the right-hand side. And that's just by doubling the resolution. And I think this is obvious to us, but when you look at it visually, it's very apparent. So I would establish that, yes, resolution, again, is necessary, but may not be sufficient, right? Okay, let's move on to the next point that I think is very important to consider when we're talking about mobile mapping and imaging. It's spatial accuracy, right? So the beauty of spherical imaging is capturing that amazing image with the detail you need at the resolution you need, but you need to know how you bring that together with your geospatial positioning information. That's highly critical to make this information you're capturing relevant. And when we talk about spatial accuracy, it's about recognizing where is that object that you see in the image and where it is in reality. Where is it actually located? So why do we talk about spatial accuracy? Well, we all know, or if you're not aware, these are manufactured systems. And so there are inherent errors in every manufactured system. So if you take lenses, optical lenses, there's distortion in every manufactured lens. And so how do you account for that? Let me just check with several of you. How many of you are familiar with the concept of astigmatism? Yeah, a few nodding heads, okay. But if just to share with everyone else, some of us, you might be like me, you're wearing glasses. When you go see an eye doctor, they're going to go and measure how well you can focus in the center of your eye. But some of us, like myself, the curvature of my lens, of my eyeball, is not perfectly curved. I might have some variations, and therefore, although it might be sharp in the center of the image, around it may not be all sharp in the entire plane that I can see with my eye. It's the same thing with the camera and the lenses. And just like your eye doctor can provide a prescription to correct for astigmatism with your eyeglasses or your contact lenses, we can do the same thing with optics and lenses. We calibrate cameras, the sensor, and the lens. We measure that distortion, and when we feed those factors into a geometric model, what many of you may be aware of camera intrinsics, the geometry with the relation between the lens and the sensor in a camera, we can feed those parameters and then correct for those distortions every time we generate an image. So this is really critical when you talk about mobile mapping and you're capturing that image. Not only do you need to know the position of the camera at the time you took the image, but can you account for the distortion in the lens so that everything you see down to the pixel level is corrected as best possible. All right. Now we talked about the spatial accuracy, but again, you're moving. So how do you ensure that you're capturing the image correctly? Well, now it's a matter of timing. And so within a system, there are systems like GPS systems or GNSS devices with an IMU. So you know where you are at any point in time. And what you want to do is you want to know consistently between the time that you trigger capture of the camera or a camera frame and the image, at that point in time, what is the relevant information with respect to the geospatial position that you're capturing from other sensor data? And therefore, if you can actually determine, or from a technical perspective, you say deterministically, you know that that difference between the trigger time and when you actually capture the image is consistent every time, then you can align that or register it with the geospatial information you got from the GPS unit. And now you have the position of the camera at the time that the GPS signal was received, and now you have spatially accurate information from between the sensor and the lens at the time you captured the image. Now you can get down to the image and pixel level of spatial accuracy of every bit of data that you're capturing during the mobile mapping process. Does that make sense to everybody? Okay. Now, what else is really critical? Of course, image quality is very critical. And there are many aspects of how you would consider image quality. But remember, what we're trying to do with this image data is we're trying to extract information. We're trying to extract information that's relevant to a client that's going to use it to make some sort of decision further down on the process. Now, today, this information is being scaled up using, computer vision algorithms, AI tools to extract that information. So image quality is extremely important. Why? Because you're going to go in there and you're going to segment the scene. You're going to look at the segment and recognize if it matches an object that you're interested in, and then you're going to classify that object. You might then perform further downstream image assessment of that object to determine its condition, for example. So aspects like your ability to be sensitive to the dynamic range of all the information that you capture in that scene, from bright to dark, is very critical to be able to classify that object. How about the color accuracy? Sometimes you may have objects that look similar, but you discern what type of object because of its color information. Or image sharpness. You want to be able to have as much information that's relevant to you in this application to be in the depth of field of your optical system. So these are all aspects that affect image quality. But let's look at this at the next level of detail. Let's get down to the pixel level. What else happens at the pixel level? What are all the aspects that help us derive the actual value down to the individual pixel? Well, for those of you that are familiar with the sensors, CMOS sensors and a Bayer filter, we have to go and in our image processing pipeline, we have to derive the color value for every single pixel. So there's a debayering process that is used to interpolate that value, and there are different algorithms or methods to do that. there is a resampling process. So you may have captured the image from a certain, from the raw pixel value, and we've corrected it by using what we call the camera intrinsics, and we correct it for the distortion. So we're resampling the image to properly represent that image data. And then there's compression. That may happen as you're trying to optimize the bandwidth transmission or the storage of that content. All of those things affect the image quality and the pixel values. You can get blockiness, you can get what they call aliasing along diagonal and edge lines. These are all characteristics that I'm sure many of you may have seen when you've looked at images close up. So what have we done? We have continued to perform research and development in this field. We've been in this field for a long time, but the technology and what we can deliver for our customers continues to advance. So we have actually done the research on a wide variety of latest algorithms and incorporated them actually into our production pipeline to deliver cleaner, more natural detail as an end result. Are all of you ready to do what my colleagues call pixel peeping? Squinting a little bit just to look at what you can actually now get out of these new algorithms? All right, let's have a look. So, okay, we're going to look at this scene here. And in this scene, we're about 4 to 6 meters away from that electrical utility box you can see on the right-hand side, and that yellow grating you can see on the right-hand side. So we're going to zoom in on that really close, okay? Can you see in this image the numbers here on the labeling of the identifier of this utility box? How on the left-hand side, this was the best that we could do before we updated our new algorithmic capabilities. And you can see along the letters, along the edge, there's a little bit of aliasing. But if you look on the right-hand side, that algorithm has produced much more natural characters, especially you can see between the white and the black edges of the characters. So that's a major improvement in what we're able to bring down at the pixel level. Another example is looking at the grading and the vertical lines. Remember we talked about aliasing and whenever there's edges and contrast in those edges? It's the same thing here. You can see some of the aliasing along the vertical lines on the left-hand side, but on the right-hand side, it's much cleaner. And I promise you, this is not being photoshopped. This is directly out of the image processing pipeline, out of our software. Right? So this is what you can see coming right out of our software by taking advantage of new algorithm developments. Are you ready for another one? This one is a little bit further away. It's about 20 meters away, and we love examples like this because it is brightly lit, but there's signage and characters that make it really interesting for us to examine. So we're going to zoom in on a couple areas right over here. So in particular, we've got some signage, and then we can see the bracket of this fence posting here. Now, it might be hard to see from where you're sitting, but again, the characters and some of the color that's being generated by the algorithm on the left-hand side of the pixels, you can see it's much more clean on the right-hand side. And then on the bottom, you can see the aliasing on the left of that bracket. On the right-hand side, the algorithm has made a significant difference. I'm going to keep moving here. All right, another one here. Now we're going to really push the limit. We're 100 meters away now, okay? And we're going to zoom way off into the distance on the right-hand side. If you look in here, we're looking at the balcony on the top image. Originally, when we looked at the image, all we could see is that balcony looked like it had metal grating on there, right? But with the new algorithms, we can actually see that it is metal framework on that balcony with the metal pattern. And on the bottom right, you see the window vertical blinds. Again, similar to what we saw, the yellow grading we saw earlier. That is much better, but we're 100 meters away. So that is quite an improvement in what we're capable to do. Now let's talk about this for a moment, about the value chain and why this matters. On the left-hand side, we're talking about the imaging capability of the sensor and the system for mobile mapping. But on the right-hand side, it's all the way about delivering the value, the information that you can extract for that decision maker. And that decision maker may never even look at the images. So at the very beginning of the process, you want the maximum image quality that you can derive to extract the optimal information in the fastest period of time that is required for that critical decision maker. And to wrap this up, we started about asking the question, what if image resolution is not enough? And we highlighted, or I postulated, that what you need is usable, geospatially accurate data. What we identified is resolution is necessary, but not sufficient. You also need spatial accuracy, you need timing, and you need image quality. And when you can bring all of that together to contribute to the mobile mapping process, then you can deliver on making faster data-driven decisions by those key people that are trying to help us in our greater society. So really quickly, I'm part of an organization called Teledyne. We are made up of multiple business segments. In particular, as I mentioned, I work for the digital imaging segment. We have products that are in the air, on the ground, underwater, and even in outer space. Those images on the right-hand side for that Mars Perseverance landing, those are the first live broadcast of a manned spacecraft ever landing on another planet. Those images are cameras that were designed and manufactured in the facility that I work at. And so I manage a product line called the Ladybug spherical imaging system. It is the leading spherical imaging system for mobile mapping, designed to operate in all weather conditions, and it has this spatial accuracy of plus or minus 2 millimeters at 10-meter distance. We've been doing this for several decades. That product line has been around for over 22 years. We're on version 6, the Ladybug 6 of this product, where we've deployed thousands of units worldwide. We're very proud of that, and of course, by any means, if you have any questions about mobile mapping, spherical imaging, and the value that it can bring, or you want to learn more about the products that our company can help, and we have several innovations that we're introducing at the show, please come visit us at our booth here, right in the center on this floor. Thank you very much for your time, and enjoy the rest of the show.